Hi, this time we are again another time in section B and designing circuits of this kind, structural circuits from the initial truth table. And what we have in mind now is to go through the idea of using only NAND and perhaps constraining even more the requirements. Just for example, designing circuits using only NAND, but the NANDs to be only 2 input. So in this way, we can start, for example, the example that we had the other day, the one that was based on sum of products, the circuit 3, and we can change the circuit 3 equations, the sum of products, to be a different equation which is going to generate the circuit 5 based only in using NAND gates. And perhaps later we can go to the circuit 5B in this way. And alternatively, we can just take another canonical circuit, for example, the circuit 1, which was solved using maxterms, and transform the maxterms so that we generate the circuit 8, which is based only in NOR gates. And naturally, from here you can go on and on, making any kind of equation, right? Okay, so let's go continuing with this series of designing now architectures again, but this time they are going to be based on only NOR circuits. So only one type of gate is allowed here in the structure of the circuit, or just only NAND, that way. So you have, for example, the typical truth table. We have to do that, of taking a table as an example. So why not again the same table, which is defined as always a product of maxterms or a sum of minterms like this. So we've got the symbols, and what we have in mind now, according to the plan that we've been explaining before, is to go from the circuit 3 that was based on the simplified equation sum of products. So now let's transform again the circuit 3 to become the circuit 5, so that it has only gates of this type, only NAND. And there is another exercise here that you can do later if you like. There is the obtention of the circuit B, for example, used based on only NOR. This time from the circuit 1, which was the original one that was based on product of maxterms, the canonical expression. So that is the definition of this C function based on maxterms. So in some way or another, the problem is quite algebraic here, because there is only about the idea of applying some algebra trick, okay? For example, you may say that y is just x if you not and not again, nothing happens. It's the same expression, right? So it's something that's simple. What we have to do to get, for example, from these, sum of products, to get gates of the same kind which are NAND, you simply have to go like this: D1 not, D0 not, A not, B not, or D1 A B, or D0 A B not, or D0 A not B. This is what you've got. The problem that you've got here, if you like to use only NAND, the NAND is something like this. It is a gate like this. So there is only AND here, and this is OR. So we are going to do that thing of noting twice the equation. So now, using the Moore theorem, we can just replace one of the nots by this idea of x, y, z. Not is just x, or x, or is just x not and y not. and Z not and not. You see, and this is an AND. Alright? You see, you have here a OR, and then you've got an AND, simply getting this kind of transformation here. So now you can imagine that this is the term X, this is the term Y, Z, and W. So C becomes D1 naught, and D0 naught, and A naught, and B naught, naught, and D1 AB naught, and D0 AB naught, naught, and D0 A naught B naught, and finally you see there is the last one here remaining, so there is another big bracket here which is the final naught. So now you see you have, in this way you can imagine very well now and then not. So this is an AND of 4 inputs, and this is another NAND of 3 inputs. So in the end, you see, you have another NAND of 3 inputs. So that's it. In the end, now, if you like, you can draw this circuit in paper as in the example PDF notes that you have on the unit, okay? Now that you've got this, there is only the idea of drawing it, you know, the way we used to do that all the time. You have the literals as usual, okay, D1, D1 naught, D0, D0 naught, A naught, and B naught. So this is going to be, for example, the term you see now is an AND of 4 inputs, so you have to connect D1 naught, D0 naught, A naught, and B naught. So that's the term, you see, and with the others the same. Perhaps here there is the idea as well that you have in mind to invent a buffer or a non-inverter circuit or a inverter circuit, not using NANDs, because those are circuits that can be implemented as well using NANDs. For example, if you like to invent a buffer like this, you better take a NAND, okay, and you connect both inputs together, so that's X and that's Y, which is X like this, you see, so this is X, this is X naught, alright. So now just another one of the same kind and the same connection, if you like. So this is X again, right? Well, X naught and naught, which is equivalent, you may say so logically, electrically no, but you know, logically this is X. So this is a way to invent a buffer. And you know, this connection can be the other way. You can have an AND, and this is X, and then the other input can be connected to a level that is not disturbing the logic function, is not blocking the gate. So this level that is doing nothing here is a 1, right? So you have X and Y like X naught. So this circuit is equivalent to the inverter that you like to find here. X, you see, you've got X, and then you like to generate Y equal X naught. So that's another way to do it. So you have this possibility or that one. Doesn't matter very much. So you have the level of literals based on NANDs, and then you have the second level of gates based on NANDs, and finally the third level of gates, which had to be OR, but this time the OR is replaced by a NAND. Okay, that's a way to do that. So let's continue now that we've finished with the circuit 5. Let's take the circuit 8 as another example. Okay, this time is the same function C, but let's imagine that is based on maxterms. So the maxterms can be expressed like this: M1 and M2 and M3 and M4, M7, M8, M9, M10, and finally and M12. That's the product of the different maxterms that we've got here. And the maxterm 3, for example, is D1 or D0 or A or B, and because the 3 is in binary 0, 0, 1, 1, you know that now, because it's a maxterm, is a term like this. This is the maxterm that we have to consider here. So very well, what if we like to design the circuit that consists of only NOR? What is what we have to do? Well, basically what you see here is that that's an OR, right? So it's not a problem. You already have ORs everywhere inside, you know, in the composition of every single maxterm you have the OR. But you know, here you have ANDs. So this AND has to be transformed into a NOR. And how are you going to do that? Well, in the same way as before. If you have something like X, Y, Z, or this is AND, you know, if you've got that, you can use the same tactical thing. You can invert twice the same expression and nothing happens logically. So now this is X naught or Y naught or Z naught, and there is the final inversion here that is going to give you the idea of a not or, because that's the or. Okay, so not or. So this is the transformation that we will apply here to transform all these products, all these ANDs into ORs. And that is almost immediate because you only have to take the full expression. You see, let's take the full expression as here in this example and invert 2 times. And if you do that, you can start now rewriting the C function as M1 not or M2 not or M3 not or M4 not M7, M8, M9, M10, and finally or M12, not in every term, and the final not. So what is this exactly? Well, this is D1 or D0 or A or B, and because it's a 4 is 0, 1, 0, 0, so this is the term that you've got here. And you see what happens now? You have a not. So this is nothing but what you can recognize very well as a NOR of 4 inputs. Okay, a NOR of 4 inputs. And finally, you see here you have a final NOR. All these becomes a NOR of 1, 2, 3, 4, 5, 6, 7, 8, 9 inputs. That's it. Okay, so that's the transformation, something very simple. And now you can start drawing the circuit as we did before. Okay, if you like, you can do the same as before, paying attention to the literals that are connected to buffers and not gates. So for example, if this happens to be the D1, and you have this couple of gates here, D1 not, D0, D0 not, A not, B and B not. If you've got that, the final circuit is, you see, many terms, but all of the same time, all of the same type. This time, all are very regular because we are talking about maxterms, and the maxterms has all of them 4 inputs. So what you've got here is a second level of gates, which is composed of, you know, 4 input NORs. So let's do that one. For example, this is going to be the M4 NOT. right? You can name them this way. If you have a wire, you can name it like this, for example. So, or if you have to write that in VHDL, that is inconvenient. So in VHDL, this may be named M4_L. If you have to give that wire a name, you can use this. So what is going to be this equation here? So the max term 4 is D1, D0 not, A and B, right? 4 inputs NOR. And you have, you know, all of them 1, 2, 3, 4, 5, 6, 7, 8, 9. You have 9 terms the same way, okay? And finally, there is this 9 input, okay, that you can represent this way. So this is the final C that you are inventing here, okay? So this is a circuit that has NORs everywhere in the 3 levels, because in the first level you can apply the same tactical thing as before. If you are liking to invent a buffer or a NOT, no problem, you can use a NOR of 2 inputs this way exactly, or and then another one, you know, another one connected in the same way, and this is the buffer. Okay, or if you have a single one, you can do the same thing, or instead you can use a convenient level at the input that is not going to block the gate. And if you have a NOR, the level that is not going to block the gate is a connection to the 0 level. So this is going to be X and this is going to be Y. You see, X or 0, that way. Not, and this is X not, which is exactly what you want, to invent a not like this. So every single not here or buffer can be replaced very well by NORs. So in the end you have a circuit that consists of only NOR, and that's the solution. Okay, that was very practical some decades ago when the people like to have only a single chip in the lab. So you buy chips like this, only type NOR, and that doesn't matter very much because you can invent a very regular circuit the same way that when you are using the tactical thing, which is, or the typical thing, which is, for example, like here, not buffer, first level of gates, and then ORs and AND. So this is the typical not buffer, all right, not buffer, and then there is the OR, and then this is the final AND. So you see, this is what you are replacing. All these different chips are going to be replaced by simply chips of this type, NOR. Okay, and then there is a last example if you like to complicate a little bit the things. Okay, there is another constraint that we can discuss here, but that is not going to be difficult. But you can expect that there is this other question. Okay, what if I ask you now, yes, right, let's invent a circuit that is based on only NOR, but let's solve all the NORs to be NOR 2. How can you do that? Well, so that is perhaps the last example, okay? Or I guess that in the initial slides, instead of NORs, we did that thing of transforming the circuit 5 into the circuit 5B. It's the same thing, you see? This one is based on NAND. So now let's transform the circuit 5 into something that is only NAND 2. It's the same idea, alright? So this, you see, here you are a NOR of 9 inputs. So how can you transform a NOR of 9 inputs into a circuit that consists of only NOR of 2 inputs? or here you are 1, 2, 3, 4 terms. So here you had what was a third level of gauge, which was like this, you see, a final NAND 4. So how can do that? Think of X, Y, Z, and W, and this is B. How can you invent this B, which is X, Y, Z, W, and a final not? How can you do that in a way that this gate can be replaced by NAND 2? That's the problem to solve. So this is not difficult because you only have to pay attention to grouping the inputs. So this expression can be solved like this. You keep the brackets, okay, but now you do x, y, just two inputs, and z, w. Nothing has happened yet. But now, if you like, I can take this and that this way. I can add here extra brackets, parentheses like this, and nothing happens. And I can do something else now, you see, because this is and, okay? So what if I not every one of those two terms? Nothing happens, you see. I go and complicate the circuit like this. So that is finally X and Y. You see what I'm trying to do here? I'm trying to identify NAND 2. This is what I have in my mind. So X, Y, not, and then another not. Okay, so this is already a NAND 2, while the other one is an inverter, a NOT, that can be solved using a NAND 2 the same way. So what you see here is the same, Z and W is the same thing. So finally now perhaps it's better to, well, let me finish this, and Z, W, not, and don't forget the last one, which is this one here. So you have, you see, it's not that simple if you like. A single gate is replaced by some of them. I guess that 5 gates. So let's draw them all now. Let's take another color and let's draw the circuit here, because this is what is left. So you have an AND to organize X and Y. So this is the term X and Y not. Then you have another one, just like this if you like. So this is the not, okay? Then you have to do the same for the other terms, Z and W. So this is Z and W not, and another gate here, do the job of inverting, okay? And finally what you see is another, okay, this is just, if you like, this is P, Q, and not. So this is the wire P, this is the wire Q, and so what? What is left is a final and NAND of 2 inputs. So you see, in the end, this is what you call V, okay? So this symbol, okay, this symbol here, I like this thing of marking and setting aside the symbol that we are talking here about. This is the symbol that we are talking about, and NAND 4 can be replaced. You have the same ports, X, Y, Z, and W, and the output port B. So you see, this symbol can be perfectly well replaced by that other symbol. So that's the lesson, right? And that has to be solved for every single NAND that has more than 2 inputs. And that way, so in the end, the circuit becomes a circuit that is very constrained. It is a circuit based on only NAND of 2 inputs, and that, you know, you have here one level of gates, if you like. This gate here of 4 input NAND is one level of gate, and that one, which is the same logic equivalency, now has 1, 2 and 3 levels of gates, and that is going to take more time to execute the computing of the function, you see. And this is something that the levels of gates involved in a given circuit is something that we will talk about in the next project 4. Well, when we go finishing the chapter on combinational circuits, that is when, and we had a lot of circuits in mind of all types, we will talk again about this idea of speed of computing. But you can imagine now that if you can realize, you can synthesize a gate like this, a NAND 4 inputs, as a single circuit, that one is going to be faster. Solving the NAND for truth table is going to be 3 times faster than this one here, because here the signal has to go from one level of gates to the next and to the next to get the same table, V, alright? Perhaps there is only one thing left here, the idea that you can go from any equation to only NAND or from any equation to only NOR, doesn't matter the initial equation that you take to do that adaptation. For example, here, what we've been doing now is considering this sum of products as transferable to an equation that is based on only NAND. This is what we've been doing now, right? Or that one. This is an equation which is a product of sums. So what we did is to transform directly the circuit, you know, doing this, okay? Click, click, and doing that, what you get is simply from this sum of products an equation which is based on only NOR, because you are the last not, okay, this second not, what is going to do is to transform this AND into ORs. That is the logical thing to do, but that is not the only thing to do. If you like, you can transform this equation, for example, to only NAND, if you like. In which way? Well, the equation looks like this, you see, D1 or D0 or A naught, D0 or A or B naught. Then the third term is D1 naught or D0 or B. The fourth D1 or A naught or B naught. And the last one D0 naught or A or B. That's the equation, okay? See. So what if you now like to use only NAND? Well, you've got the AND already here. So this is what we called the AND. So the AND is already here. So what is left to transfer this AND of several terms into an AND? So not very much is left to do here. You simply have, you see, X, Y, Z, W, and V. This is what you've got here. So what you can do to get an AND is simply invert it to transfer the AND into an AND. You invert it one time, and then there is another gate that does the job of keeping the logic expression the same, but using two NANDs, you see? The first one here, and the last one, so, which is a NOT. That's a way to do it, okay? And then what? Well, there are plenty of ORs, you see? You have a lot of ORs everywhere, OR gates. In every single sum you have plenty of ORs. So, and you like to have NANDs. So what is the point here? How can you do that? Well, you can do something similar as you did for the total expression, but now you can do that X click click, Y click click, not not, not not. You can do that perfectly well and nothing happens. You see, logically it's exactly the same expression. But now, if you do that not not, what is left from this factor, you see, is exactly that one. D1 not, not, and D0 not, and B not, and a single final not. So what is this if not D1 and D0 not, B not? What is this if not, you see, another NAND? So that's the point. Any expression can be converted to only NAND or only NOR. It doesn't matter which is the original one. Perhaps this one has another level of gauge. That is true. The last inversion represents that you've got the circuit, and the end you have to knot it completely, so that adds another level of gauge, a fourth level of gauge. But if you are not paying attention to this, you have that this expression, which is a sum of products, can be solved not only using NOR, as we did before, but using NAND. You see, and the same with the other one. If you are now using this other C, okay, if you are now working with the other C, the C becomes D1 naught, D0 naught, A naught, B naught, or D1 AB, or D0 AB naught, okay, and finally D0 A naught B. This is the expression that you have. And what we did before is to generate an only NAND expression, inverting it twice, converting every single OR into an AND. So that was the natural thing to do, if you like. But what if I ask you now to use or transform this expression so it is based on only NOR? Well, so you can do something very similar here as this previous example. What you've got here is X or Y or Z or W. So only NOR, right? So OR. Now you've got the OR everywhere, the OR. So what is to get the NOR? What is required? Well, you can invert one time and another time. You see? That's the way. Alright? No problem. So you have a gate which is that one, X, Y, Z, W, and now you have this NOR, you see, and finally you have another NOR like this, for example. If you prefer the circuit, so this is going to be the C the same, okay? Being this X, this Y, this Z, and this W. So that's the final ending of the circuit. And now what is left here, because you see you are interested in ORs, you have plenty of ANDs. That's the point. You have ANDs in every product. So the AND, you see how to transform the AND into a OR. So that means that, for example, you can use this term, for example, okay, this way. This is Y, and Y becomes D1 A B and. So what if now you simply because what you want is a OR, so what you do such a thing as this, not not, not not, not not, not not. Every one of these terms, every one of these products can be not twice and nothing happen, the same as we did here. But now, you see, this term, the Y, is not, and then is not again. So what happens here? Well, the Y becomes D1 not, or A not, or B not, and a final not. So what is this if not, something to connect here, which is nothing but another NOR of 3 inputs. So that's the point, you see, another NOR of 3 inputs, so that's the solution. Whatever the expression you have, there is always this possibility to get what you want, a final circuit based on only NOR or only NAND. You see, there is always a possibility, so what I recommend you to do now is to do that to the end. Take a sheet of paper, as usual, and finish it out of the class, you know, in your own way. Try to finish this until you get the big idea here, which is, you know, this time, because of these forced transformations, you have another level of gates. This was the third level of gates, and this is the fourth level of gates. You have this extra inverter here, or that way is the same. You see, you have here this inverter, which is the same idea of the fourth level of gates. But doesn't matter, in the end you have the circuit that you want.